maybe now we can start. Good afternoon and welcome to our fifth seminar. And today's topic is hydrogen utilization technologies. This is our fifth seminar, part of our hydrogen seminar series organized by the Clean Combustion Research Center. Today our moderator is Professor Mani Sarati. He's Professor of Chemical Engineering and Associate Director of Clean Combustion Research Center. Before we just go, there are two more seminars coming, one on November 22nd on building hydrogen infrastructure, and the other one on December 6th on the policy options for hydrogen deployment. I would like to take this opportunity before I forget to thank the CCRC communication and admin team again for their help and support, the CAUST IT also team. So without any further ado, I would like to welcome Professor Mani.
Okay, hi, good afternoon, everybody. So welcome to the Hydrogen Seminar Series. We have three excellent speakers today. We'll be talking about hydrogen utilization technologies. This follows on our former seminars related to production, storage, transport, as well as safety. And of course, the utilization of hydrogen, the technologies available, the market, upcoming or forthcoming for hydrogen utilization globally is very important. So I'm very happy that we have three really world-class speakers, Professor Doug McFarlane, Professor Bassam Dali, and Dr. Lee, and all three are experts in hydrogen utilization technologies. We'll start today's seminar with Professor Doug McFarlane, who's joining us online. Professor McFarlane is a distinguished professor and formerly the Australian Lord Fellow at Monash University, a global expert in the area of materials chemistry and electrochemistry with specific focus on renewable energy generation and storage. He has well over 800 papers. He's a highly cited researcher. He was the Australian Academy of Science Craig Medalist in 2018, and also the winner of the Victoria Prize for Science and Innovation. He has a spin-out company, and I hope we will hear about that, Jupiter Ionics, which aims to scale up ammonia production that he developed in his group. So, Professor Doug McFarlane, we're happy to have you.
All right. Well, thank you for the kind introduction. Let me just start off by sharing my slides, get this organized. And I guess if I do that, okay, that looks good, I think, hopefully. Right. So thank you for the introduction. I hope I'm not going to be too disruptive with this talk, in the sense that I'm in the end going to talk about an alternate to hydrogen as well as a utilization for hydrogen. So that's open for discussion, shall we say. Okay. So let me get right into it. I think most people here will be familiar with the concept of a map like this, which shows totals. This is for solar energy, and there's similar maps for wind. That convinces that certain parts of the world, you can see that the very dark colors around most of Australia also includes, of course, parts of Western and Southern Saudi Arabia there, Northwest Mexico and Southwest of the US, etc. These are very highly intense solar irradiation parts of the world, and are capable of generating enormous amounts of electricity. For example, that little square on the map of Australia, and you could put a similar one somewhere in Saudi Arabia, of course, can generate on that land area 250 by 250 kilometers, an amount of electricity with standard commercial solar cells, an amount of electricity, 25 petawatt hours per year, which is the electric supply of the whole world. So that just illustrates that there's plenty of energy around if we can figure out how to, well, we know how to harvest it, but that's what that land area looks like in Australia, of course. It's a lot of that very empty area is cattle farming. But the issue is how to how to move it out of these remote regions, typically in remote regions, to the populous markets, in our case, to the north. Or to put it rather simplistically, what's in that boat in the middle of my picture? What's in that ship? Is it hydrogen? Is it ammonia? Is it something else? Okay, so that's kind of what my talk is very much about tonight. Just to illustrate how significant Japan is in this, you might notice the big arrow leading up to Japan in my map. This is a picture from just before COVID created lockdowns here in Melbourne, of a major deputation of Japanese government people visiting our labs to find out what was going on with ammonia. And that's getting on for 3 years ago now. So to dive right into this, I just want to illustrate to you the green ammonia picture that is emerging. First of all, we call Generation 1, Gen 1 ammonia is green ammonia is the traditional process, which is called Haber-Bosch. It's a big chemical engineering process. Runs on natural gas today, and with carbon capture, that could be rendered somewhat less climate offensive, and that's often, of course, called blue ammonia because it's captured fossil carbon. Moving on from that, there's the prospect here we can use green hydrogen. If we have green hydrogen from electrolysis or some other process, we can put that into the Haber-Bosch process and generate ammonia. And then to put ammonia into some context as a liquid as a fuel, let me tell you that it can be liquefied at 12 bar of pressure at 30 degrees C. So that's the kind of pressures and temperatures and so on for LPG. So think of that kind of engineering, nothing terribly complex there. And as that liquid form, it has an energy density of about half. That number there is about half the megajoules per kilogram of gasoline. Okay, so it's not going to ever be a long-haul jet fuel because it's just not energy dense enough, but it in fact is being considered as a short-haul jet fuel. So it's energy dense enough to be a sensible fuel in its own right. However, before the world got to that point, I've just given you kind of the most up-to-date 2022 thinking there, but before we got there, there is clearly a role for ammonia as a hydrogen carrier. In other words, as I've just talked about, we can make ammonia from green hydrogen. Shipping of ammonia, this is why it became the focus of attention. Shipping and pipelining of ammonia is routine. There are several technologies around now to turn ammonia back into hydrogen, or crack it, as we say. And then, of course, the hydrogen is available. Maybe that fill station is in the middle of Tokyo, and that cracking is happening underground under that fill station to fill that Toyota Mirai hydrogen fuel cell car that there's a picture. I think I'm in the middle of that picture driving that car. So that's ammonia as a hydrogen carrier. It's in the supply chain. It starts with hydrogen. It ends up with hydrogen, but ammonia is the thing that's in the ship. However, that idea, if you like, stimulated quite a lot of further discussion, and many of us were reminded that, in fact, not so very long ago, ammonia has been used as a fuel in ordinary engines. Think of ordinary diesel-type engines. As far back as Belgium in the Second World War, there was a fleet of buses running around, running on ammonia, and you can see in this picture the cylinders of ammonia sitting on top of the bus. Okay, so ammonia used directly, no hydrogen in this, the rest of my story. Apologies to all the hydrogen people here. Ammonia directly as a fuel. Right up to date, here's an ammonia power turbine that is very similar to a natural gas turbine running on, that is tweaked, if you like, tuned to run on ammonia. That's not a major refit of that turbine. And this whole situation was considerably propelled by the International Maritime Organization mandating that shipping, the commercial shipping of the world, should aim to be effectively carbon neutral by 2050. And as the shipping companies of the world and the ship builders of the world began to look around for what that fuel might be that was going to replace bunker fuel, then the answer, really the only answer that was viable was ammonia. And that has largely taken root as the main way forward for international shipping. And that is a huge amount of energy required for shipping, especially by 2050. So that's a little sort of quick little summary of how that's developing as an end of supply chain utilization of ammonia that might have started with green hydrogen as the thing that was stimulating the production of the ammonia. But I want to then go on tonight and talk about again, apologies to the hydrogen people here, but talk about, can we effectively skip the hydrogen and go direct to ammonia from nitrogen? And the electrolysis approach to that, to answering that question, is relatively similar to the electrolysis that produces hydrogen. So to the extent that we're talking of an electrolysis type hydrogen, it can be, in concept, can be turned over into an ammonia producing process. Nitrogen being delivered into the cathode where reduction takes place. And instead of making hydrogen, hopefully, we will make ammonia. That's the goal. That's the concept here. And in fact, thermodynamically, this is quite sensible. Chemists amongst us here will so some people might be quite surprised at this. I'll have to say I was when I first came across this, that in fact, despite the tremendous stability that we all know of the nitrogen molecule, the thermodynamically reducing it to ammonia is actually easier thermodynamically than reducing protons to hydrogen. So 0.3 volts easier is the way that is what that slide is telling us. However, the key point here is that we need to be keeping an eye on the hydrogen reaction, because we don't really want a mixture of hydrogen and ammonia, and those two numbers are rather close. And in fact, there's a problem here, because nitrogen is not very soluble in most solvents. And if we're thinking about carrying out our electrolysis in water to make ammonia, then we're always going to have a problem with the reduction of water itself, because there's so much of it, and that makes hydrogen. So hydrogen, in fact, is a major challenge in this concept. So I could talk for quite a long time about how that challenge has played out in the world, and then it's not a pretty story. But so I'm going to just leap to the last couple of years and say that there is an alternate, or an approach to allow us to avoid this hydrogen problem largely, is to switch to non-aqueous solvents. And in this case, we're dealing with ether type solvents or carbonate type solvents that are similar to what's used in a lithium battery. And in fact, this approach that we call lithium mediated has got many elements in common with the lithium battery. So lithium battery people would recognize some of the story here. So without going into this in great detail, I'll simply say that some of this was known when we dived into it to try to improve the process and make it efficient. And one of the key things that we had to do was to fix up this what was this compound called B, which is some sort of base, carries the protons from anode to cathode. But what is it, and can it be stable? And we hypothesized that this rather complicated looking bit of phosphonium chemistry, but it's actually quite well known. This is an industrial chemical in the surfactants business, so made in large quantities, actually does this job rather well. And I won't dwell on the chemistry here, but let's just say as a component in this story, this is executing this black cycle in the cell that effectively brings in nitrogen and pushes out ammonia in this electrolysis cell. So to show you some very up-to-date results, I have here, let me just check the time. Yeah, I have here some results that were published in Nature just about a month or so ago, where for the first time, what was really a big deal in this paper was that we were able to show for the first time in this teal color, Faradaic efficiency of nearly 100%, effectively 100%, as close as we can actually measure. And what this is effectively the selectivity of the process towards making ammonia and not anything else, including hydrogen, right? So we are achieving that goal that I set for ourselves a few slides ago of making ammonia efficiently with nothing else. If anything else is happening, this is usually bad. So this has always been a high priority milestone in this field. At the same time, these two properties, the yield on the other side and the slope of the black dots gives you a yield rate. How much ammonia are we making? And in the red lettering, you see that this particular experiment, which is just a laboratory experiment, is making the equivalent of roughly 2 kilograms of ammonia per square meter of electrode per day. And that was a stepping stone, if you like, to becoming practical. And I won't dwell on the energy numbers there, but I can talk more about that if somebody would like to know, because I will say there are issues there are challenges there. But this did springboard us towards setting up a spin-out company. This is called Jupiter Ionics, and if anybody wonders what is the role of Jupiter in this, it is that for the astronomers and Star Trek people amongst us, Jupiter has an atmosphere that is almost entirely ammonia. So there's the link. And our goal there is to scale up from that Mark III iPhone-sized cell that you see in the top left through what we call that middle one is called the fridge, and then the shipping container. And the shipping container is the sort of quantity that some of the very big farms in Australia would like to have to make fertilizer on site. That one of those is a big farm type productivity of ammonia. And then to scale that up into the gigawatt realm, of course, the aluminium industry teaches us how to do that with electrochemistry, which is rather than just a bigger and bigger cell, we make just lots of them, what is otherwise called the pot line. So we would have an ammonia pot line, which could produce more than 5 gigatons of, not gigatons, sorry, 5,000 tons of ammonia per annum. So let me just finish here by showing you a picture of us actually using some of our green ammonia. We reckon this might have been the first ever genuinely green renewable produced ammonia actually used as a fertilizer. Here we're fertilizing a cucumber plant, which we subsequently ate. And I'm still, the cucumber that is, and I'm still here to tell the tale. So it was all good. So with that, I will finish, and hopefully I've stayed on time, and look forward to some discussion later on.
Yes, so we'll have a discussion and questions afterwards. I'd like to introduce our second speaker, Professor Bassem Ghali, who's coming from here in KAUST. He's a professor of mechanical engineer and a member of the Clean Combustion Research Center. And over the last 30 years, he's led major research groups and initiatives around studying various thermal fluid related topics, including plasma propulsion, soot in flames, mild combustion, also hybrid concentrated solar thermal applications with thermal energy systems. And more recently, he's been focusing on the utilization of hydrogen and ammonia fuels for various industrial applications for decarbonization. He has some large projects in Australia as well as here in KAUST to this end. And he's been an Energy Professional of the Year in South Australia and a prestigious fellow of the Combustion Institute. Looking forward to your talk, Bassem.
Thank you, Manny. I hope people online can hear me as well. Following with what Doug has said, hydrogen and ammonia are sort of go hand in hand. Sometimes we refer to hydrogen and its derivatives. Doug, you could produce ammonia and then reduce it back to hydrogen if you need hydrogen as well. But what I'm going to focus on is the potential role of hydrogen in decarbonizing heavy industry, as a session sort of more about utilization. And here's a figure basically that I came up with, looking at what are the options to decarbonize industry and heavy industry in particular. And in there, you could see that I listed iron and steel, cement, alumina, and petrochemicals. And in a minute, I'll show you why. And then looked at what are the options. So direct electrification has been told as the way to go. Let's electrify everything. Of course, that is not the right approach, because you need to be able to store all this electricity in the first place. And if you're coming through a solar or a other means or renewable fuels, you'd rather use it directly than convert it into electricity. But nonetheless, direct electrification does have a role. And in there are listed for each one of the industries what the potential technologies are and at what TRL they are, technology readiness level. Next one is solar thermal. It has an advantage of storing energy at relatively cost-effective ways, but it's yet to evolve and develop, although the development in China is actually making a big difference in solar thermal. The other two is hydrogen and ammonia. And I put ammonia in there as well because, of course, you could produce ammonia from hydrogen, or as Doug showed, you could actually produce ammonia directly through this process that he described from water and nitrogen. So in there, you'd see that hydrogen can be used both as a heat source and as a reductant. So either it's a chemical or as a source of energy. And almost each one of these applications. And the last one is biofuels, and the issue with biofuels is always will be scale and seasonal variability. I promised to show you why iron and steel, cement, and petrochemical are important. If I list here the countries and their emission for 2020 in terms of CO2, and you could see if iron and steel was a country, it'll be number 3 in the world. Cement will be number 4, and petrochemical will be somewhere sort of between 4 and 5. Now, of course, some of the emission of these countries is dependent on iron ore and cement and so on. It's included within. But what I'm trying to highlight in here that these are industries or sectors that substantially produce CO2, and hence they are important to be considered separately as such. So hydrogen is versatile, and this is why it's actually really important. You could either use it for power and heat generation, and you could see here some of the options how you could do that. You could use it as an industry feedstock or as a chemical, basically, as ammonia production, steel production, synthetic gas, hydrocracking, hydrogenation, and so on, and or for transport. You could see in there that you could use it for fuel cells, for example, forklifts. It's becoming quite common actually to use it indoors because it does not emit any harmful gases and it's only steam or water. Hydrogen-powered vehicles, hydrogen-powered trains. I'm not sure about aircrafts, but ships also. But of course, we could always say hydrogen and its derivatives as well. But you could see that you could have one fuel that could do lots of things for you. Here's how hydrogen being consumed these days. You could see that 25% of it is going into petroleum refining. You could see that around 10% goes into methanol production, around 55% into ammonia production, and out of this, almost a majority of it comes from source of fossil fuels. 90+% come from natural gas. So you take natural gas, you're reforming to hydrogen, and then but that basically, if you don't capture the CO2, you have carbon emission, and the rest going for transport and other applications. So this is what's happening today. But if we to actually use more of the hydrogen into decarbonization, some of these numbers are going to change substantially as well. So these are some other uses. It's not restricted to what I showed you in there. You could use it in food, you could metalworking, welding, flat glass production, electronics, manufacturing, or medical applications. And here you could read it for yourself, but there's a lot of applications for hydrogen beyond just sort of the way we're seeing as fuel cells, for example, or some other applications. But here, hydrogen is actually quite a versatile chemical that can be used in lots of applications. So let me start about options in using hydrogen for decarbonizations. The first and the easiest way is hydrogen blending. And what's hydrogen blending? Simply you come and say, I have a system operating on natural gas. I simply want to add hydrogen to the natural gas. And so this way, it's what's called fuel displacement. In other words, instead of burning this amount of this fossil fuel, I'm burning less of that fossil fuel. The good thing about that, as the advantages here listed, is it's basically give you fuel flexibility. When it's available, you could put it in. When it's not, it's not. And let's face it that in the transition for the next 10, 20 or more years, there will be ups and downs. And also will be a fluctuation in the market. One day you have cheap hydrogen or expensive natural gas and so on. So having an option actually will be good. At low concentration, no major changes required. Simply you blend it in, and I'll show you a map showing what the percentage it is. Allows for intermittent supply, use when available, basically. Increase familiarity in using and handling hydrogen. If eventually hydrogen is going to be the fuel of choice, it'll be good to then start, learning how to use it, start using it in our systems. Then eventually, when we switch to full 100% hydrogen, we're already familiar with it. And so this is basically a transitional approach to utilize existing systems. Why do I need to throw all my infrastructure out and put a new one? I could use what I have in the transition until I actually then switch to something else. In terms of disadvantages, the concentration that you could use is actually limited without making major changes. So on average, and it changes quite a bit, it's less than 20% by volume. Now, as you know, hydrogen is very light, so 20% by volume is not a lot in terms of energy. Yeah. Additional capex with limited carbon reduction, because the energy offsetting is small, then you're not saving a lot of carbon. Nonetheless, you're saving some carbon. Change in flame characteristics and potentially NOx emission. The flame will change if you're adding some hydrogen to it. Metering, suitability of piping and safety concerns. Metering, suddenly now you have a mixture. Is your current metering sort of accurate or not? Are your pipes can handle hydrogen or not? Leaks are a major issue for hydrogen, so is all the pipes actually suitable, and so on. And then it's a short-term fix that will have a limited time. It's not a solution for the future. So here's a map basically adopted from a European study showing how much we could blend in terms of hydrogen, natural gas, and get away with it if you want in between brackets. So the green is basically, it's harmless. In other words, you could add up to this amount, and then you don't need to do major changes. Next one is after technical check feasibility. In other words, you need to do some trial and errors or basically checking. And the next one is basically we don't know and research is needed. So if you start in transport in here, you'd see that sort of in the transmission pipelines up to 30%, there won't be any issues. And then gas turbines, really very small amounts. And again, this is by volume, so it's not a lot in terms of energy. And then we move into compressor stations and so on. And then in terms of storage, again, not much you could add unless it's specifically designed for it. Metering and pressure regulations, again, there's issues in there at high concentration. And then distribution, and then in terms of utilization. And sort of, because today we're looking at utilization, you could see sort of the line between 10 to 20 at max is in fact less than 20 most of the time. So in Australia, for example, there's a trial in Adelaide where they're adding 3.5% hydrogen to an existing natural gas pipeline. And they verified that the appliances at homes work with that with no actual issues. So blending is one aspect. That's quick. You could do it tomorrow if you want. All right, another important part is the iron and steel. And then with iron and steel, there is basically either one step or two steps. So the two steps is basically, let me show you in here, the processes of doing it. So basically, you take an ore and you convert the hematite, which is Fe2O3, into magnetite. And to do that, you need an agent and a reductant. In most cases, they use carbon for that. So if you look at on the right side, you have the oxygen concentration. On the left side, you have the carbon concentration. And you could see through this blast furnace, you put a lot of carbon in to create this hematite. And from there, you use the basic oxygen furnace to basically convert it back into steel. But notice how the temperature is quite high, and you melt everything, and basically the steel comes out sort of runny as water, with all these slag sort of floating on the top. The other approach, which is sort of a more modern approach, is what's called a DRI, direct reduction of iron. And there sort of you could operate, you don't have to melt to that temperature. You could operate basically at a lower temperature. And when from there on, you could also use electric arc furnace to basically convert it into steel. And the third option is what is a term sort of plasma reduction or hydrogen plasma smelting and reduction, where you could go for ore almost straight into steel without needing any carbon, at least for now. So for the first two, which basically what we call a two-step approach, CO2 will be emitted because you're using some carbon. Please note that for DRI, currently, syngas is being used. You bring natural gas, you compare it to syngas, and eventually out of that, CO2 will emerge. And by the way, this is a simplistic look. It's much more complex than that, but just for you to understand what the issues are. So as I said, the hydrogen plasma reduction is basically one step. So in a single step process, we have a project in here. Jordan is one of the students and working with Professor Diana Lacoste as well, looking at how can we basically use plasma and hydrogen to reduce the iron to what we want it to be. So the advantages is basically no need for pre-processing, sintering, or pelletizing of the iron ore. The energy reduction is 55%. And this is the key, by the way, that if we smart enough, decarbonization can be cost neutral. And if we could do that, then the saving in energy can basically pay for the decarbonization of the other options, if you want. The other major advantage is that you could use low-grade ore. So DRI would only work when the concentration of iron in the ore is 69% and above. With this plasma reduction, it can be lower than that. And of course, you're not emitting any CO2 because you're using hydrogen in the process. There's advantages, of course, in here in terms of the energy level required when you go into the plasma, and this is where your savings come from. And then so you have negative Gibbs free energy, and then the temperature sort of will help also in the melting point as well. Options in terms of advantage in DS Spanish currently, sort of if you use an arc type system to generate the discharge for the plasma, then some of it is going to be consumed, and the scaling is a major issue. I won't dwell on that, just to highlight that this is a technology that we're looking at developing. We're not the first people to work on this, by the way, but we have new ideas of how to basically take this approach, get rid of the anode, and then they use inductive plasma to be able to do it, or some other approaches that is currently being protected under IP, to be able then to use hydrogen for the reduction. So what needs to be done is we need to understand the reaction rates and key steps for the reduction process. We need to sort of better the mechanism of reduction and the interdependency of the plasma and particles. One thing is to create a plasma. Another, if you have in-flight particles inside, then that's another issue. Actuation strategy, hydrogen is not the easiest gas to create plasma from. That we need to see how we could do that effectively or efficiently, and the scale-up process is one of the major impediments that we like to tackle. So the DRI process with IAF using hydrogen is basically you start with iron ore, you pelletize it. Remember, we talked about the two-step process, and then in here you use hydrogen, and the product is going to be water. Remember, we're removing oxygen from the ore, and that will create basically water. And then eventually, sort of melting iron will be in an electric arc furnace. And the thing is, this is requires a lot, because sintering requires a lot of amount of energy. It requires high-grade iron ore, as I mentioned before. So, for example, here in Saudi Arabia, the best ore available has 43% iron in it. It's a two-step process, and sour camphor may still be used. So they even talking about adding some CO into the system because they're not getting full conversions. This is just a comparison between the actual process blast furnace and the what's called a hybrid. So hybrid is a commercial system, pilot scale being demonstrated in Sweden, and basically using hydrogen or green hydrogen for that. So you'd see here electricity is creating hydrogen, and that then it's used. And on the right side in there, my left, you could see the CO2 budget. and you're ending up with small amounts, around 25 kilogram per ton of steel produced, or rough steel. So ammonia can also be used. So if hydrogen is not available and we shipping ammonia around, here's a process by which nitrogen can be used. There's issues of reactions and which need to be tackled, but it's another option by which we could eventually turn iron ore into Fe, basically. And here's another thing. So one thing is creating the iron, another one is the steel, and in there you need a lot of heat to preheat. So we came up with the idea of using hydrogen to replace fossil-based fuels. But the thing is, in most of these heating furnaces, radiation is used. Now, as compared to fossil-based fuels, hydrogen does not emit a lot of radiation. So we came up with an approach of actually doping the hydrogen flame with 1 or 2 or 3% of aromatic hydrocarbon. And then this will create soot within the flame envelope. This soot will be burned before it leaves, but it does actually radiate a lot of its energy out. So we could then use hydrogen for reheat furnaces. So it's a retrofitting approach, but still it's using hydrogen. And because you're lowering the flame temperature, you're likely to lower NOx as well. And you could also use bio-oil-derived aromatics instead of using sort of fossil-based. And then you have still a CO2 neutral approach. Here's a matrix. I won't dwell too much. I think I'm running out of time. But this is sort of how do you reduce CO2 emission from iron making. Of course, the top part is about carbon capture. This is the easiest approach. I'll go to the exhaust and basically capture the carbon. I could use it or store it. The next is basically the different technologies I talked about. It gives you sort of the years until how mature the technology is, number of years until you could get productive again, and then development cost, capex, operating cost, public acceptance, and so on. So basically, these are all the options, and you could see that the plasma component is still sort of many years ago, while others are readily available today. Cement and lime. So these three ways we could do it. 60% of the CO2 comes from the material. You take limestone and you compare it into calcium oxide, and by this you release CO2. Then the other 40% is basically from energy. You need all of this energy to actually do the reduction of the calcination, and then the capture up to 80%. You could do it using really expensive sort of processes. So the calcination process is you taking calcium carbonate and you turn it into basically calcium oxide. And you could see in here that you need high temperature for this to happen. And then you have to capture the CO2 from the exhaust. The cost of the capture ranges from $30 to $100. I put $100 in here, but it can be as expensive as that. Currently, a mean-based system is estimated at $65 a kilogram, but that varies quite a bit. One option is to use oxy-fuel, by which we remove the nitrogen from the oxidant before we start. Again, this is not a cheap option, but it's one option to concentrate the CO2 in the exhaust and make it easier to capture. The other one is steam calcination. So in other words, instead of burning fossil fuels to provide the heat, we could basically burn hydrogen, and this will give us sort of steam, and steam is a good heat transfer fluid. So what you end up in the exhaust is CO2 and steam. You condense the steam and you collect the CO2. Here's a process that we patented, basically doing exactly that, steam calcination process. And basically what I want to do is to take a liter of water. I want to put it through an electrolyzer. I want to crack some of it, end up with hydrogen, oxygen, and the rest of the water. I want to react it back again and create the steam at the temperature required. Of course, it's easily said and done, but the idea here that renewable energy will be used to create what I call green steam. So using requires lower temperature and hence reduces energy per ton. Hydrogen and oxygen can be produced by electrolysis, as I've said. Condensing the steam, then we'll leave a pure stream of CO2. So we've done some Aspen Plus modeling. more than 90% of the water is recycled, and that's important, of course, and that 94% of the CO2 can be captured, which is much higher than I showed you before in the previous processes. Technology is financially competitive with natural gas plus capture when hydrogen cost reaches around $2 a kilogram. And the aim is to get to $1 a kilogram. I know that this process also applies to magnesite, bauxite, kaolin, clay, and so on, so it can be applied to other ores. I won't dwell too much here, but this is sort of some of the calculations we did, and depending on the price of natural gas, where it would be competitive and so on. The good thing about renewables, by the way, is that you're not hostage to the cost of fuel. The players in the market is going to change, where you do a lot of capex investment from the start, knowing you're going to get returns for the next 25, 30 years, and then you know exactly how much hydrogen it's going to cost you. So in other words, you are a little bit in control in terms of the cost as compared to a current system. If anybody monitors the natural gas prices, it's a seesaw basically, and the difference between them can be up to a really big number. And again, in here we're looking at cost of lime. So limestone is the. You could also use lime itself. It doesn't necessarily cement. And you could see in here if you do steam calcination with air separation unit, if you do it without air separation unit, oxy-fuel process, and so on. So comparisons what the cost would be, and it doesn't look like it's sort of hugely expensive as certain percentages increase, but that depends totally on the fuel cost at the end. Finally, power generation. So here's are some of the options. Industry requires a lot of power. Some of it they generate themselves. Gas turbines, diesel engines, fuel cells, boilers, and then hybrids with renewables. I listed the TRL and what are the issues. So the gas turbines are relatively efficient under hydrogen, could stretch the boundaries quite a bit. NOx emission could be an issue. Diesel engines, I'm not sure about NOx emissions, but can be. Of course, it's retrofitable, and that's important. Fuel cells, there's issue with durability. Boilers, currently they're using basically ammonia with coal. And ammonia, of course, can be produced from hydrogen. And this hybrid idea is that you could use hydrogen as a long-term storage or seasonal storage, and to give you a firm supply. So I have hydrogen, I could use it whenever I need to. And then when maximize the use of the solar resource. So this is still low TRL. I'll show you some work that we've done. Basically, we took a cavity receiver, and then we installed burners inside, and then we ran this using a variety of fuel. And if you could see on the figure in there, we ran a syngas, H2CO, we ran hydrogen itself, and then we looked at the efficiency, the maximum temperature, and basically it works quite well. So efficient operation on 3 modes, and 3 modes here are solar only, combustion only, or mixed mode. And you could see here up to 90% efficiency and more than 750 degrees C. Lower solar fluxes can be used to supplement combustion. And then convective losses through aperture is less than 50% if there's no earth. So we actually can have some gains in there. Here's basically a summary of what future R&D for hydrogen utilization industry required. That's something I came up with for steam generations. I listed from, say, today up to 2035, what will be required, where R&D is green, and then demonstrations, and eventually sort of deployment, if you want. And then in there, sort of, I talked about blending. I talked about hydrogen, oxygen, water, sort of steam generation, and so on. How sort of modifying DRI can help by adding more hydrogen to it, or later on at much larger scale, sort of further on, what you could do with plasma as well. The kiln, so lime and cement with this technology of steam calcination, and with heating furnaces, what we could do as well. And here's the conclusions. Technology is not a barrier to utilize hydrogen in industry. Blending hydrogen with ammonia and ammonia with fossil fuel is a good transitional step. Scaling, piloting, and deployment are needed in the next decade. Further research and development is needed to exploit promising technologies like the one I showed you. Fuel flexibility and blending is the most plausible option in the short term. That's sort of repeating some of what I said before. hydrogen production for industry and at scale would need to be on site to minimize cost and transport and storage, and synergy in niche applications. There's a lot of people wanting green metals, so are essential to develop know-how, expertise, and de-risk large-scale adaptation. Thank you for your attention. I'll finish here.
Okay, thank you, Professor Dali. So the final speaker is Dr. Taewon Lee. Dr. Lee has a PhD in electrochemical engineering from Columbia University and more than 30 years of experience in the fuel cell industry in both the United States and Korea. In the US, at Fuel Cell Energy, he participated in the development of molten carbonate fuel cells. And in Korea, he was the head of the Center for Chemical Engineering for Doosan Heavy Industries and also the CTO for POSCO Energy. In 2018, Dr. Lee founded Fuel Cell Innovations, which is a joint venture between Saudi Arabia and Korea, aiming to develop SOFC, solid oxide fuel cell technology, and electrolyzer technology for these countries. So we're very excited to see what Dr. Lee has in plan with his Fuel Cell Innovations. Dr. Lee, we can see your screen. Thank you.
All right, thank you. Thank you for inviting me for the this venue, and also thank you for professors for the good informations. Let me go to the other my slides. Okay, I have 3 parts. I just want to introduce 1 page of slide about our company, and tonight I want to actually focus on the products for MENA region, and I'll conclude with the product development status in our company. As introduced, this company is more like a spin-off from POSCO. POSCO is the largest steel company in Korea as well as in Asia, and we had actually more than 20 years of the fuel cell developments, and but it has been spin off with the other SOFC technology a while ago, and then after that, this company is actually invested by S-Oil and Aramco and Taknia Energy, which are the Saudi companies, and Samsung. We have actually commercialized our product recently, and we are planning to build Gigafactory by 2027. Our technology platform, I'm from the other industry, and I'm really focusing on the products and the business model, so that how our technology can be converted to the other certain area, especially matching to the other energy structure of the region. We have actually developed MCFC for more than 20 years, and our SFC also about the other 15 years. Now those technology are converted to FCI, and for the SFC, we think that the SFC and the SOE are the same classification because we use the same common stacks and the cells. And the MCFC, we are moving to the other second generation of the other MCFC. These are our technology platform, and also we are able to integrate ESS, which is lithium iron phosphate battery, and because these are, and the PMFC, that's polymer electrolytes membrane fuel cells. Those are important because we aim to make hybrid systems with these 2 products. So we have some SFC product here and also MCFC. Through the last 15 years of the business in Korea, Korea is a very special country for fuel cells because we have very strong subsidy programs in Korea. We experienced to install 172 megawatts of the MCFC fuel cell power plants. And through our experience in the field, we developed expert system based on AI algorithm for the control and the optimal operation of the plants and the fleet management. Let me start with the other two focus. Two things that I want to focus. That MENA country, as everybody knows, the strong dependence on the fossil fuel, which makes the necessity to capture the carbon to make the other clean energy in the near future. And also, another aspect is the cost of the oil and gas is very cheap. So based on these two, this is very challenging. This is very challenging actually to have the other fuel cells as a good product for MENA region, but the capex is the most clearly the other important thing that we really need to reduce to the bottom. But the one good aspect is the high ratio of the other LCOE or even LCOH versus gas price is still high, which means Saudi and the US and the UK and the Germany, it shows that the index of the other, which is the ratio of the LCOE versus gas price, which means that the margin for the value proposition to sell the products is still green because it's high compared to any other countries. But contrarily, in Korea and in Japan and in China, the value is much lower, which means that the subsidy program is required to promote industry. So this is the situation, and we focus on three things. Carbon capture products and very low capex, which is only possible by localization of the production in Saudi or any region in MENA. And also another thing that I want to really focus on tonight's presentation is hybridization of the other certain processes. So those are the other major focus of the other tonight's today's actually. Here it is night. This is the R&D priority in National Hydrogen Strategy in PSA. The strategic advantage and the criticality for the development. This fuel cell and the electrolyzer technology can cover wide variety of the very important business models or technologies, which is actually for the SFC and the MCFC for carbon capture or green hydrogen production, and also ammonia fuel and ammonia fueled ships, marine fuel here, and SOE hybrid for e-fuel and e-chemicals. Those are the what we started to develop, and for the certain models, we already came up to the other small or medium scale of the other commercial products. As I said before, S-Oil is the oil company, the largest oil company in Korea, and Aramco has also value chain of the hydrogen and also ammonia, and there was the MOU between these two companies, and these two companies are our shareholder, major shareholder actually. And then, so S-Oil already decided to develop and deploy and promote the fuel cell business in Korea as well as in Asia or any other regions. And this is the way that the SFC or SOE can be used for the hydrogen and ammonia value chain. It is a wide variety of the applications, from starting with the production and also transportation, and also here, I don't mean the other any compression or phase change of the other materials, nothing like this. Only the other ship application for the transportation of the ammonia and hydrogen. And also the final utilization of the hydrogen and ammonia by fuel cell is very obvious. It is like a power generation and also hydrogen generation. Let me go over our proprietary technology quickly. As a spin-off company from POSCO Energy and the West, we transferred the 16 patents on SFC, and that technology was accumulated for 17 years by spending more than $200 million on R&D. We came up to the 10 kilowatts and 25 kilowatt stacks when I was the CTO of the company. And now we made some advancement of the 10 kilowatt single stack. For SOFC commercialization, single stack is very important because we connect single stacks in parallel or in series to make the large stack and the large module for SOFC and SOE. We have seen our small scale stacks started to last more than 30,000 hours, and also we made some advancements on the coatings and other applications of the new technologies, and we are aiming for 5 to 7 years of the durability. Molten carbonate fuel cell technology. There is only one company who's making the products and do the business in the world, that is Fuel Cell Energy in the United States, where I worked several years, a long time ago. Also, the molten carbonate fuel cell technology has been developed also in Korea from 1996. There are two different ways of the commercialization. Internal reforming MCFC was developed by United States, and the external reforming MCFC was developed by Korea and Japan. We have both technologies in-house. Years ago, only internal reforming molten carbonate fuel cell was valuable for the commercialized products, because in those days, the needs for the hydrogen fuel or ammonia fuel was not that the importance. But nowadays, ammonia fuel, direct ammonia fuel for fuel cells, or hydrogen, or even LPG fuel, these are only also possible for the internal, external reforming molten carbonate fuel cell. And we know how to make the fusion of these internal and external reforming fuel cells. And we are also very interested in the mixed fuel, blended fuel with hydrogen and also ammonia. Another technology we are working on is the molten carbonate fuel cell and the SOFC solid oxide fuel cell cascade. So mother stack is molten carbonate fuel cell, and the solid oxide fuel cell is a daughter stack. Molten carbonate fuel cell has the lower fuel utilization usually for the commercial applications. SOFC is different. So compensating any drawbacks of these two technologies and into one, and make the BOP systems for just the one, integrate the BOP, gives us the huge advantage of that. So that's also the other technology and which we can commercialize. These small product, SFC product for homes are on sale, and also this 45 kilowatt system for data center and the buildings are also on sale. And this is made, and this is going to be field operation early next year, and will be on the market next year. And this is the product for the Saudi market, the MENA market. This one can be used LPG and also LNG and ammonia mix. For now, I can say only 27% of the ammonia will be okay with hydrogen or with LPG. Our roadmap for the core products. This is what we have for SOE, which is the solid oxide electrolyzer. We have done 5 kilowatts hydrogen in the lab scale, and we started to develop here the larger scale with our larger 30 kilowatt common module, and we will have higher than 1 ton hydrogen production per day. We aim to have it in 2026 for the markets. And the SFC is on track to go for the megawatt scale, because Korea is a very unique country where the government provides a subsidy for the other power generation by fuel cells, any types of the fuel cells over 100 kilowatts. And the subsidy lasts for 20 years, so that there's a very good business model in Korea. SOE commercialization, as already I said that, we focus on the 3 business models. E-fuel for MENA country, nuclear power plant linked SOE. We can have plenty of the high temperature steam from the nuclear power plant, because nuclear power plants was designed with 7% surplus steam generation, and we can use them for the production of the hydrogen. And also SFC and SOE hybrid system for CO2 capture, which I will introduce. But before that, ammonia application, we focus on the direct ammonia. Just ammonia is a direct fuel, and then we don't need to really crack the ammonia to hydrogen, and then we can have the other much higher efficiency for the other power generation. There are still a couple of the other issues that we need to solve, but for now, some the mixed fuel for the other SFC is working fine for the other SFC, and we are developing the catalysts and the special coating to prevent the nitration and many other corrosive reactions. So ships, I can explain that later here in the slides. We started long time ago for the molten carbonate fuel cell for ships. It didn't work very much. We switched it to from 2020 to use solid oxide fuel cell, which is much smaller and lighter compared to the molten carbonate fuel cell. In 2020, and several months ago, we completed the first phase of our R&D, and this 40 kilowatts SFC is a hybrid system with gas engine and the ESS system to supply the power for the propulsion of the ship. It was successful projects, and then we are expanding our project for the 500 kilowatt SFC system. This will be the commercial product right away, because we can do some kind of other powers for the hybridization, and that they will go for the markets. So in 2028, we aim to have the other 20 megawatt commercial ships to apply that. And here, this ship is being constructed in Korea. Korea is strong for the other shipbuilding industry, and this is already designed, and this project will be applied for this ship, and we bring the SFC to the ship. And the important thing is that the ammonia fueled SFC is also a very important topic for Korean government. So that this project will be funded by Korean government for 5 years. This is also the other what we designed based on our patents. This number here, okay, I have 2 cases of the new hybrid processes here. SFC for the power and hydrogen co-production by using PSA and the special controls and special catalytic oxidizers, and also sometimes we already designed the oxy combustor that will be used actually for this process, SFC and the SOE hybrid for the power and hydrogen. These 2, we believe, are the very good commercial model for industry and for the other, especially for the MENA countries. As we know that 60% of the CO2 is captured from the fuel, then the hydrogen produced from the process can be identified as the blue hydrogen. And this actually we target on the higher than 85% of the other capture of the CO2. And for this one, we aim actually 95 or even almost all the other CO2 from the other fuel, as well as we have a very special patent on here, like when we use the other air for the combustion, the huge amount of the nitrogen is fed in there. And then the separation of the CO2 is very costly and very difficult. So what we do is use oxygen, which is the byproducts from the SOE system, so that the hydrogen will be our products, but oxygen will be fed to SFC system, and then the CO2 will be recycled, or even we can feed other CO2 source to the SFC system, and we capture and we can go for the carbon negativity, which means that we capture the CO2 from the fuel, as well as the some other sources of the CO2 from the industry to make it negativity of the carbon. I just want to just quickly show that why this process, blue hydrogen production process is economic. This is the steam methane reforming, which is already commercialized, and the large plant is being built in Canada and United States and also in Japan. Simply, we burn LNG to feed to supply heat for the reformer. In our system, solid oxide fuel cell, we get a co-production of the power and hydrogen. Here, we use the reaction heat from the SFC, which is high enough because the system is operating at the temperature of higher than 730. So there is enough supply of the heat from the reaction, and then we don't need the combustion here. So internal reforming SFC can be converted to the internal reformer of the LNG to produce blue hydrogen, and then some of the power can be generated, but most of the fuel can be separated for the hydrogen as a hydrogen. So we can say that there's a blue hydrogen, and also we can do the modulated operation between power and the blue hydrogen. That kind of functionality is also very important for the industrial applications. And theoretically, we aim LCOH target is compared to conventional SMR system that can be about the 27 or 28% lower. So if I summarize that by doing this, we can do increase the efficiency much higher, and the CO2 can be captured by up to 95%, so even more. So this is also a very good technology, we think, to bring it to the other industry. So let me summarize that our company is a JV between Saudi and Korea. We are supposed to provide solutions for the hydrogen and the carbon neutrality and the carbon negativity by using fuel cells and the electrolyzer technologies. We are actually preparing the mega gigafactory which is the automated production of the gigawatt scale. That makes we aim to produce the fuel cells below $1,700 per kilowatts, and we have the global R&D consortium. Especially, we have a very strong and active cooperation with the research institute in Swiss, Sion, and also a couple of universities in the United States. And we really want to extend our open innovation consortium for the R&D also to MENA countries. So we are open for that. And we have the multiple fuel cell technology, which is based on the solid oxide fuel cell and molten carbonate fuel cell. And that's it. This is my contact, and I hope that we can make this opportunity to be aligned together for the other cooperation in R&D and the product development. Thank you very much.
Thank you, Dr. Lee. Okay, we have time now for some discussion or questions. Are there any questions from the audience for any of our speakers? Professor McFarland, Professor Dali, Dr. Lee? Okay, Professor McFarland, yes, thank you for your presentation. I had a question regarding the overall energetics of the process, if you looked at it. So for your system, I guess you need an ASU to get the pure nitrogen. Then I was wondering then if you include that and then the energy required for the reaction, how does it look overall compared to a conventional water electrolysis and ammonia Haber-Bosch?
Good question. There was some data on one of my slides, but I won't try to bring them back up. So to give you a sort of an overview answer, the lithium mediated process that I described there is a bit of a brute force process to actually break open the nitrogen molecule. So it is quite energy consuming, and to use if I use energy efficiency numbers and including the air separation stage, which is common to any, well, no, I'll come back to the air separation point in a moment, actually, but let's just say that we include an appropriate air separation stage. Then our energy efficiency at the moment, we're looking at around about 25% electricity energy in, ammonia, lower heating value energy out, effectively. Now, that compares with estimates for the overall electrolysis green hydrogen, not including any kind of storage, but pumping to pressure, because Haber-Bosch requires elevated pressures, and then the Haber-Bosch process of combining all of those somewhat energy consuming steps. A little bit hard to get really concrete numbers on this, but shall we say, probably going to turn out between 40 and 50% is where it looks at the moment. So you can see we're not there yet. Yeah.
And what happens to the oxygen in the cell?
So again, good question. So our anode reaction similar to water electrolysis on the anode, is water oxidation to oxygen, so oxygen evolution, and that we currently simply let go. We get rid of that.
Okay,
But
thank
of
you.
course, that does have some value.
Yeah.
And perhaps I'll just quickly come back to that point about the air separation stage that you mentioned. Again, that's an important aspect of this, which is that the Haber-Bosch process requires very pure nitrogen and hydrogen. So both have to be purified with respect to oxygen and water to a strong degree. Electrolysis hydrogen, of course, has a challenge in that regard, before that gas can get to the Haber-Bosch catalyst, okay, which is sensitive to those gases in a lifetime sense. We don't have that kind of problem. So the air separation technology that we're thinking of is quite a lot simpler and less energy hungry than the cryogenic separation that's currently used with Haber-Bosch.
Right. Okay. There's just a follow-up question to you that came online. Professor McFarland it's asking, when do you think this ammonia container, and I'm assuming the production container, would be available to farmers?
We have farmers in Australia asking us that question quite frequently, especially since fertilizer prices have gone through the roof in recent times. So we are planning to have a first somewhat smaller scale, more like that fridge version that I showed you, 1 kilogram a day, a version of that as a prototype on a farm in northern Victoria, a grape growing farm, by spring next year. So that's about a year from now, just a little less than a year from now. Once we kind of iron out the wrinkles in that, there might be an intermediate stage before we prototype before we get to the ton a day size. So we're going from 1 kilogram a day to a ton a day is a very big step, of course. So we'll probably have an intermediate stage prototype, which is still useful at some level of farming. The ton a day is for very large farms, what we call broad acre grain type farms. So I didn't answer your question, sorry, not entirely. So I think that's going to be a few years away. Let's say 2 to 3 years away.
Doug.
Okay, thank you, Professor McFarland. I'd like to go to Dr. Lee. I'm working on a project here in Saudi Arabia called NEOM, and we do a lot of things related to hydrogen, but also off-grid power. And we face some challenges when evaluating SOFC technology. One, for prime power, meaning when you need backup power in some applications, the time delay to get started up on an SOFC can be rather long. So cycling can be a challenge, and also in the temperature that we have here, it's sometimes challenging for an SOFC to compete with a PEM for backup power applications. So I'm just wondering, what are your main market and or do you have some solutions for backup power with SOFC technology?
India, the MENA region, as well as the India, our first target market is the telecom backup, actually. And it can be done because we have developed the 99.99% availability products for data center, and I believe that will work for the other telecom markets and also buildings. Only thing is that the faster operation or some kind of power modulation for the special cases or the emergency cases, that can be actually a little bit enforced by some kind of other hybridization, and we have tested all those options, and I think it's doable. It is expensive, but if we had the other targets for the other several regions like India or MENA regions and many other countries, then with just the modification for the regional safety regulations and the certifications, then we can make the product much cheaper than we expected.
Okay, thank you. We have a question here from the audience.
Professor Douglas, thank you for your presentation. Very exciting. One question: how your technology compares in terms of cost? You know, the NRR, the nitrogen reduction, reaction technology versus the Haber-Bosch. It seems that very interesting because this is high pressure, high temperature. You are moving to modest pressure temperatures. You are using air, electricity, water, I think, as input. You are using renewables. It seems that it's net zero. The other technology emitting CO2. So overall, if you include the CO2 capture, how would it compare in terms of cost? Dollars per kg ammonia.
Yeah, it's quite a complex question. That the first big factor to discuss is the energy, the cost of energy that goes into that calculation, right? Given the greater energy cost of our process compared to green hydrogen plus Haber-Bosch or Gen 1, well, that's a sort of a different calculation, because of course it's the cost of natural gas that goes into that one, and then the cost of the carbon capture. So that's a different equation. But if you think of the green hydrogen plus Haber-Bosch calculation, of course we are more energy costly, therefore the cost of energy is a sensitive factor in our process. So we're doing modeling, and others have done this too at this stage on this. And what you see is, as the cost of renewables comes down, especially this is of great interest to a lot of the farmers that I was talking about, a behind the meter situation, so that the farmers or the production company is generating the supply locally and feeding it directly in. Especially, an important point to mention is that this electrochemistry process is able to wind up and down according to the supply of renewables. So it can follow intermittency in a way that is somewhat more difficult with Haber-Bosch technology. So there are some problems in that Haber-Bosch concept to deal with intermittency. So the price of the power going in is a big variable here, depending on how that's costed. On the other hand, as you, I think, hinted, it's clearly a capital cost less intensive device that we're talking about, compared to the combination of water electrolysis cell, which is mechanically somewhat similar to our cell, plus the whole Haber-Bosch technology that goes with it, with the Gen 2 modes. So complicated techno-economic analysis there, which is very sensitive to that price of energy. So in summary, the lower the price of energy, the more our sort of technology begins to look like the winner.
I have a question for Professor Dali. A very interesting technology for the steam calcination, and very promising in terms of price competitiveness at $2.20 per kilogram of hydrogen to make it comparable to fossil fuels. So then what is the barrier? Is this a technologically proven process, or are there still barriers towards raising the TRL?
I think at this stage, it's really engineering barriers, material suitability at the temperature required, and at the pressure. So theoretically, it should work and actually have major advantages. The trials that were done by Calix technology in Australia showed some promise, with some technical difficulties related mostly to material. That's not unsolvable in a way. There's also an approach of hybridization, and in other words, you could do half of sort of steam as compared to something else, and add it to, for example, electric heating as well. So we're keen to build a prototype and to test, and we believe that once we overcome these technical difficulties, we should be able to reap the benefits out of the advantages from the energy point of view.
Okay, thank you. We'll take one final question from the audience, and then I will close the session.
The question is to Dr. Lee. Thank you for the presentation. It was very wonderful to see some developments in solid oxide fuel cells. I just wanted to understand what is the operating temperatures of your SOFCs, and what is the kind of, to reach those temperatures, where do you get the energy from to ensure that SOFC starts performing efficiently? And in slide 15, you did share that instead of SMRs, you are trying to replace them with SOE, solid oxide electrolyzers, and which means that the electrolyzers need to have certain amount of energies again to operate, which is coming from SOFC. So on this overall aspect, how much cooling is needed, what is this operating temperatures, and what is the overall efficiencies that we are looking at in this aspect?
All right. There are many different types of the solid oxide fuel cell technologies, like electrolyzer supported cell, which is commercialized by Bloom Energy, is working at 940 degrees Celsius, I think. And ours is actually anode supported cells, and which is operated at 830. And some other cells recently developed by Sirius Power or something is even lower. We are also working on the other slightly lower. We prefer to the other slightly lower to 815, something like that. But the more important thing is that the design of the other stacks, because the thermal neutral points of the system is important, because the reaction to generate power is exothermic, so that that heat can be used to maintain the system temperature. So that usually the thermal neutral point is at around the certain, which is much below the nominal operation of the system. SOEC is a little bit different story, because that it needs to have a very high temperature steam, which should be higher than 830 or even 850. In that case, that we can increase the overall efficiency very high, and for the SOFC, for the power generation, it really depends on the temperature and the fuel utilization and the system designs, but we can come up to the other. Our system is now 55%, because we already made 60% electrical efficiency, and the total energy efficiency was designed to be 90 or 91%. But those products are for the Korea, and because for the MENA region, I need to cool down the whole cabinets and the products during the daytime, and then so the parasitic loads of the electricity is much higher than any other countries, so that efficiency should go down a little bit. When I say efficiency, which is based on the LHB and but the AC basis. SOEC efficiency is varied like 80% to even 90-something% based on how much you get a high temperature steam you provide to the system. So that's what I can explain now.
Okay. Okay, thank you very much, speakers, Dr. Lee, Professor McFarland, Professor Dali, for the nice presentation and the discussion. This seminar will be available online at the CCRC Hydrogen Seminar Series website in a couple of days. So I think it's going to be very valuable resources for many years to come. So thanks again to everybody.